Welcome all to another webinar from Diabetics. Today it's a bit of a special one as I'm joined by Ines from Avient. And today we'll be talking about generative design for thermal management of LEDs. I myself, I'm a customer support engineer at Diabetics, while Ines, perhaps you can introduce yourself.
Yes. Hi, everyone. So I'm Ines Mesmer. I'm a design engineer since 3 years into Avient company, and more precisely into Avient design team. And today, in order to illustrate the use of CoreStream, we will present a topic that we face more and more in our daily work, which is the evaluation of the feasibility of replacing aluminium into lighting application.
Thank you, Ines. For today's webinar, we'll be covering quite a lot of topics. The introduction, that's something that we did already before. Next, we'll discuss more about what Diabetics and Avient do, more respective fields. Gives you insight into how we apply both of our knowledges to then the application that we want to discuss today. We'll then move to actual case study itself, so how we tackle the problem, discuss the results. If you have any questions, we will cover them towards the end in the Q&A session. If you have any questions throughout, feel free to put them into the chat box. Our moderators are following along, so any questions can already be answered in the webinar itself. And lastly, of course, if you're curious or want to know more about both Avient or CoreStream, we'll give you some contact information towards the end. But let's start with the beginning, introduction to both our companies. Starting with Diabetics. So as Diabetics, or with Diabetics, we believe that smart algorithms can empower engineers to design beyond human imagination and to also automate the design process itself. So we strongly believe that smart algorithms can be used throughout the entire design process, so both early on as well as for towards the final end to do post-process or to do prototyping. Sorry. As you see here on the top right, ANSYS and Hexagon, two of the very big names within the CFD world, both acknowledge the strength of our software, have reached out to us, and we are their technology partners now. Our last webinar with Lieven, we mainly focused on GPU accelerated designs. That's in collaboration with ANSYS, if you're curious about it. So how does that translate into the real application? How does it translate to how you tackle problems? On the left, you see the conventional way of working, which I'm sure most of you are very, very familiar with. We'll start with an empty geometry where you allow cooling structures to be generated. You first create a CAD model, most likely do a CFD simulation or physical experiments. You process the results, analyze what needs to be changed, and you loop through this until you get a solution. Quite demanding and quite a bit of manual interventions needed. While with CoreStream, we want to linearize that process more. So early in the design cycle, CoreStream will generate a wide variety of different concepts, giving you insight into what design change affects performance, also giving you insight into its pins and fins already meet your thermal requirements or not. If no, then you can move on to then what we call the detailed design evolution to basically extract the maximum out of it. To get something similar to what you see here, something very intricate, which is beyond human imagination, of course. Moving on to Avient.
So Avient is a multinational company with around 10,000 employees worldwide, and we have more than 35,000 solutions. It's also around $4 billion in sales, and we have several establishments around the world in 35 different countries. And some people may know us by one of our former names, so Polyone or Clariant. And in short, Avient, it's a compounder that takes virgin plastic and that we enhance with different type of additives and reinforcements to give them a precise function. So the first business unit in Avient is the color additive and inks. The technical function here is the appearance of the product through color or resistant or UV and also, for example, scratches. The second axis is what is called specialty engineered materials. So we have there materials mechanically reinforced with fibers, either short, long, glass beads or continuous fibers. We have also densified materials that have a heavier density, X-ray insulation solution. We have elastomer with impact absorbent or vibration damping properties. And it's also in this category that we will find the thermally conductive plastic that we will look at today in the case study. So finally, what does Avient Design do? The team supports the customer during all its product development and is willing to evaluate the combination of design, material, and process. So it starts with the design by developing different geometries that meet the customer expectations. And then with the digital prototypes, we are evaluating the design numerically with different materials that are selected from our portfolio. It can be either looking at the performance of the part with mechanical or thermal evaluation, as in the following case study, or looking at the process through injection molding evaluation. So actually, today it is an iterative process with a lot of interaction between the design and the digital prototypes, with back and forth between those two boxes. And at the end, the goal is to get the right performance and right combination of the design and the material. The idea of using Diabatix is to let the software do those iteration on its own and to get design that met the performance criteria in few runs without iterating several times between the design and the numerical prototype. So once the design and the material are numerically validated on our daily work, many customers need prototypes to do physical tests. So this is why we are adding the prototyping capability in the team to be able to give the right design with the right material to do physical tests. So we are looking at physical and functional prototypes. So to provide those different prototypes, we have two main process. In the next slide, please. So the first process is injection in 3D printed molds. So in this case, we will 3D print a mold with thermoset resin, and then we will take Avient pellets, dry them, and inject into those 3D printed molds. It can be either injected manually or industrially into a real injection machine. The second process is called a fused layer deposition process, because this time we are using additive process. So we are taking the pellet. We can either do a filament out of those pellets to then use it on a regular 3D printers, or directly use the pellet into a 3D printer with a small extrusion screw. So now that we have give the context of what the Avient Design team is doing, we will focus on the case study. So the case study, this time we worked on the heating for LED heat dissipation, and we applied the full design simulation and prototyping process using Diabatix software. So for an aluminum heating, we took standard one from the market with a given PCB and LEDs. And the goal is to replace this aluminum with thermally conductive plastics. So of course, it's never only about heat dissipation. We have other requirements for the application, like lightweighting and cost saving. And this is where the thermoplastic that are thermally conductive can really play a role. So with thermally conductive formulation, we have a lot of design flexibility, lightweighting, lower system cost, and also fewer steps in the process compared to an aluminum heatsink, for example. And then if we look to the thermally conductivity of this material. On this small graph, you can see that aluminium and alloy has a really high thermal conductivity, around 150 to 200 watts per meter Kelvin. And the thermally conductive plastic have a lower thermal conductivity, but it's around 10 to 20. It's 10 times lower than the aluminium, but still it's really higher compared to standard plastic. So we have a functionality there in those thermal conductivity plastic that is pretty good, and we will see how the design can play a role and be able to replace aluminium heatsink. So if we move to the next slide, first, what we did is to calibrate our numerical model. So for that, we did some physical measurements. So in fact, we had already the material properties of our heatsink and PCB. We had the electrical power of our LEDs, but we were missing some important input as the thermal power and the LED material. So we did physical measurement, as you can see on the left picture, with the aluminum heatsink and the PCB. And it gave us the temperatures reached on one of the LEDs. Then on the right, you can see the numerical model, so the representation of our physical ones. And we have iterated into CoreStream to be able to get our unknowns of the studio, so the thermal power and the LED material. Once the model was validated, so we had really low percentage error from the simulation, we could move to the next step. So I will let maybe Niels go more in. No, it's not now. Sorry. So once we have validated the numerical model, we use CoreStream to generate design this time. So we have set up different criteria. The first was about the process. We wanted that the part can be injected. So we need to have draft angle, for example. We need that the part can demold, in fact. And then we have two other targets that was minimizing the design volume and also minimizing the LED temperatures. We did two different studies into CoreStream, one that is called generative design and one that is a topology optimization. So with the generative design, we are able to get around 60 designs that are really standard shapes. So it's iterating on fins and pins to get to our criteria. The topology optimization this time is giving only one design, but that can have unconventional shapes. So it's more creative, and that will really do a topology optimization, as we know.
Okay, thank you, Ines. Let's now move on to how those cases, or how to tackle that project into CoreStream. And for that, of course, I have to switch to the software. Yes. So this is a CoreStream, or at least the main landing page after you log on to the software, and as a project overview. As the name implies, it gives an overview of all your different projects to keep everything nice and organized. Inside of your project, you then define your different cases, and then the engineering problems that you want to solve. CoreStream supports three types of cases: simulation, standard design, and custom design. With simulation, that's a regular CFD simulation. As Ines mentioned, there are some validation needed to make sure that whatever is the physical reality can be translated into the simulation model, and it's also to validate if all the input makes sense. For example, buoyancy will be used. Is radiation necessary or not? If you disable radiation and see the temperatures are way too high, then you know, of course, that radiation needs to be included. So the simulation case is really useful early on to validate, does your input make sense? We then advise to move on to the standard design case. So standard designs can be used more early can be used early on in the design cycle. As Ines mentioned, Colstream will validate between more conventional cooling solutions, pins, fins, for die casting. If you allow for 3D printing, you can also look at gyroids or lidenoids, so triple repeating patterns. It might be that one of those conventional cooling solutions already meets your design criteria. Of course, then it stops. But if you want to extract the maximum out of it, then you will need to go to the custom design, where Colstream, as the name implies, of course, return a very custom design to your application. So what does the workflow look like in Colstream? If I go to the workflow view, you start by defining the base case, basically your initial geometry. You define then the simulation, the CFD simulation to validate the input. You move on to the concept generation, and if it's not sufficient, then you move on to custom designs. I will skip the simulation part and go straight to the standard design case to showcase how it works. So once you create a new case, Colstream will ask you to upload a step file. I will skip that part and go straight to the case that already has a geometry file. Yes. And then we can have a look at what we did in this case. So here there were 3 LEDs placed on the bottom with a power of 3 watts and made out of aluminum. And here, of course, it's our heat producing component. We want to maximize the thermal uniformity, maximize the heat exchange efficiency, or equivalently minimize the temperature of that heatsink. There is some thermal paste between the PCB and the heatsink, which is a custom material. The PCB itself is a solid made of aluminum. Then we have the heatsink base. In this case, of course, we will use our thermally conductive plastic from Avient. We have a design region on top. That's the volume where Colstream is allowed to modify the geometry. So everywhere within this blue box, Colstream can change the shape. And as a user, you have full control over what kind of cooling structures Colstream can consider. For example, if you look at die casting, what was used here, you can consider circular pins or rectangular fins. But as I mentioned, if you can afford 3D printing, or if you're interested in 3D printing, you can look at gyroids, Neovius shapes, split P, whatever you find fancy or want to consider. But in this case, the die casting options were selected, and then you specify what kind of manufacturing settings are used, basically to constrain what kind of structures Colstream can consider. The structures can, for example, need to be at least, just saying something, 1 millimeter thick, or the release angle needs to be at least 2 degrees to get it easily out of the mold. That's something that you can easily specify using the manufacturing settings. And of course here, weight is very important. So we put a relative volume minimization objective to let Colstream know use the least amount of weight as possible. And lastly, it's air cooled. So we define a big air box surrounding everything, where we'll use air. We will enable buoyancy to drive the natural convection motion. Where we specify then ambient conditions and the gravitation vector along -y. So that's the minus yellow arrow, so it's pointing downwards here. And of course, we'll let Colstream know how the turbulent behavior is accounted for using the K epsilon model in this example. And that's pretty much it. So once you provide all of that information, of course also the boundary conditions, the ambient conditions on the outside. Once you provide all that information, Colstream can start computing and will generate all of those options for you. So let's have a look at what Colstream did in this finished case, of course. Yes. So Colstream in this example attempted 92 different iterations, and in the Design Evolution tab we can have a look at what designs Colstream attempted. The Design Evolution tab will give you all the iterations on the x-axis and its performance on the y-axis. I'll come back to that value later on. And this should also be seen as a timestamp. So Colstream will first output the first iteration, then the second one, and so on and so on. And every iteration can have one of 3 colors. If it's red, it means it's infeasible. For example, if you have a weight constraint or you have a maximum temperature constraint and it's exceeded, then the iteration will be red. If it's blue, it means it's a feasible design, but at this stage it's not the best one. And if it's green, it means at this stage it is the best design. In this example, the first iteration was feasible. At that stage, it was the only iteration that was available, so hence it's green. Iteration 2, 3, 4, and 5 didn't improve on it, so they remain blue. Iteration 7 was again feasible. It improved on iteration 1, so hence it's made green. And then we can easily see that iteration 30, the last green dot, is the best out of all 92 different iterations. And if we scroll down, we can see that it's a thin design with these dimensions. And if we scroll down even further, you see how sensitive each of the objectives are with respect to the design change. So on the left, we have the temperature minimization objective, and basically the heat exchange efficiency, and the lower the value, of course, the better. On the right, we have the volume minimization objective, or the weight minimization objective. And the weighted sum of both of these will give me my overall performance graph. So this is the more conventional way where Colson uses more conventional cooling solutions. Let's say this design, or the last green design, doesn't meet all performance criteria just yet. We can then improve the design further by using topology optimization. I'm used to a QWERTY, this is an Azerty, I'm using Azerty, this is QWERTY. We can then create a custom design case and use this design as initialization to give Colson a push in the right direction. So now it will create a custom design case, and if you go to Start Setup, it will automatically load in the geometry from earlier, and it will keep all of my input. The input itself is for custom design is almost identical to a standard design, so I won't go through it now. And later on in the slides, we can have a look at the final design. So I'll go back to the slides. Oh, yes. And let's move on to how each of the designs perform with respect to one another and compared to aluminum, most importantly.
Yeah, thank you for the demonstration. So at the end, the next step was to select from the result from Coldstream different designs based on weight and temperatures obtained. So in the table on the left, there is a current design with aluminum, which is our reference. Then there is the same made on of thermally conductive plastic, which result in finally minus 42% in weight and only plus 5 degrees C compared to the aluminum. And the 4 other designs were created by Coldstream. So we have one selected with pins, which result of minus 82% in weight for only plus 4 degrees C. Then we have selected a middle pin design, we call it, for a weight reduction of minus 63% and only plus 3 degrees C. Then we have the high fins, which gives the better performance regarding temperatures. So we have minus 10 degrees C compared to aluminum, but in this case we have an increase in the weight reduction, so plus 60%. And then the last design was done by topology optimization. And in this case, we have around plus 9% regarding the weight for minus 8 degrees C on the PCB for the temperature. So pretty good performance. So we have selected those different designs to have a wide range of weight reduction and also thermal performances. So once we have selected those designs, we went through the prototyping step. So in the next slide, you can see what we have done. So to be fast and be able to produce such shape easily, we have selected a layer by layer deposition process, and except for the pins that was too challenging regarding the dimensions, we were able to produce parts out of those geometry with our thermally conductive plastic. So yeah, then the last step was to test those prototypes. So with the good design and the good material, and compare it to simulation. So on the results on the table, what we can see is that we have a percentage of error compared to simulation that have been calculated on the last line. We always stay below 15% for the error, which is okay. We know also that we are producing those parts with 3D printing, so we have a small difference in performance compared to an injected part, but they are pretty functional and representative of what we are getting in our simulation. So based on simulation and based on the physical measurement we did, we have pretty much the same conclusion. So for example, the high fins is always a design that gives the best performance regarding temperature, but we are not lightweighting the part with this design. And for example, the cross design is giving a pretty good equivalence to the aluminium part with a weight that is pretty the same and a thermal performance that is also pretty the same. So it's showing that using a good design with thermally conductive plastic can replace aluminium on certain application, and for LEDs, it's working pretty well. So for the next slide, I think it will be also the last. This case study has shown us the potential of thermally conductive material to replace aluminium in lighting application. So it requires some design and simulation work to find the right balance, but it's well supported by such a software as Avient-Diabatix. So in conclusion, combining the technicality of our material with design, digital tools, and also prototyping is helping us to develop new products and support our customer in those steps to go for a new product launch.
Unfortunately, looking at time, to stay within the 30-minute mark, we won't be able to do a live Q&A. Of course, feel free to keep on putting questions in the Q&A section, in the question mark section. But let's wrap the meeting up to stay within the 30-minute mark. If you're curious about Coldstream, there is a Try Now account where finished demos are available for you to have a look at and download results. Or if you want to contact the team, feel free to email to info@diabatix.com or to simply call this phone number. Of course, if you're interested in Avient, feel free to...
Yes, feel free to reach out. There is my name, but also the name of the people from my team in that work in France, so Edouard, Oscar, and myself. If you are interested in thermally conductive plastic, feel free to send us an email.
Then, yeah, last thing we want to do is thank you for your time. I hope you enjoyed it, and hope to see you in the next webinar. Have a nice day. Bye-bye.
Have a nice day. Bye.